Okay, I've got a transformer here, and I figure that my power is about 57 units a month, which means I'm using about 80 watts continuously. This transformer is 80 watts, approximately, and I'm just trying to work out how much magnetism is actually in the core. So I've got a 1.5 volt battery, and I've got a resistor. There's actually a volt on the 230 volt winding of the transformer. And so we got, I worked it all out before, there's 50 milliamps, 47 or 50 milliamps flowing through 1 volt. So if I just put this on to here, alright, well I'll just check it here with this. There's no magnetism, and you can't feel anything. You put it on this, and then straight away you can feel magnetism. Okay, there's the laminations are joined there, so there's bound to be a bit of leakage there, but you can actually feel it. You can feel it there, so this is probably slightly magnetized. This lamination has a bigger transformer. So, as far as I understand, what am I say here? When the 230 volts goes on this transformer, more current flows than just the 40 milliamps or the 50 milliamps, because it probably takes a certain instant of time to make a connection with the iron, so you get slightly more current flowing. But all you really need is 40 milliamps in the 50 milliamps in the transformer to produce the magnetism. And when the transformer's got the 230 volts on it, on the output on the other side, the only link is the magnetic field. That slightly dampens it by about 10% the magnetic field. So if you had a resonance circuit, if you had this open core and you had a resonance circuit on the main, on the 230 volt side, you could achieve resonance with the right capacitor and everything. Well, the moment you put a load on, it dampens the magnetic field by about 10%, and that breaks the resonance. So in theory, or just looking at it, overall, you should only have to increase the magnetism by about 10% to maintain resonance while you've got a load on the transformer. Because the magnetism from loaded to unloaded it only changes 10%, and there's only a very small amount of magnetism in there. It's only 50 milliamps, 1 volt across the windings, 230 volt windings. So what have we got here now? Load current almost equalizes the input, and the difference is a small link magnetic field. Like that's what you're seeing here. It's a very tiny link. Now the magnetic field that's in the core is 90 degrees out from the winding power, the power going through the transformer. So you've got input power, output load, and then this magnetism is being produced, shifting the polarity north-south, north-south, and the link 90 degrees out from the phase of the load going through the of the transformer. Now when you see what happens when the 230 volts hits the winding, the moment the magnetism in the core builds a little bit, it produces a voltage in that winding opposing any current flow. So it's called a back EMF, back electromotive force. So the moment that magnetism builds, it just creates a voltage, and it's like only about 3 volts difference, 2 or 3 volts difference. So the current in the transformer is only really being pushed by about 2 or 3 volts. Yeah, I remember good here. Yeah, well, the idea is anyhow that some way you can actually replace that 10% loss in the core 90 degrees out of phase in a particular way while the transformer's got a resonant circuit that's been driven through into a load.